last spotlight is support recovery for orthogonal matching pursuit, upper and lower bounds. The presenter is Raghav Somani.
Hello everyone, this is Raghav Somani from MSR India, and this is the joint work with Chirag Gupta at CMU, Dr. Prateek Jain and Dr. Praneeth Netrapalli at Microsoft Research Labs India. In this work, we study a simple and classical algorithm, orthogonal matching pursuit, which is very popular in the domain of compressed sensing and sparse regression. So, given a matrix A with n samples each of d dimension and an observation vector of length y, the goal is to find a sparse vector x bar, which minimizes the least squares objective. This problem is NP-hard in general, so we study it under the assumption of restricted strong convexity, RSC, which is one of the most classical and most tractable assumptions in the literature. In the standard optimization setting, the fundamental quantity that captures the hardness of the problem is called the condition number, kappa, which is defined as the ratio of smoothness and strong convexity of the objective function. Similarly, for sparse optimization, there is a restricted notion of condition number denoted by kappa tilde, which is defined as a ratio of restricted smoothness and restricted strong convexity of the objective function. We work under the model where the observation vector y is equal to the product of the measurement matrix A and an S star sparse vector x bar, along with some added noise eta. We just require some deterministic conditions on eta to hold, and in general, sub-Gaussian noise also satisfies those conditions. The goal of the problem are to bound the generalization error, also known as the excess risk. Here, the samples in A are IID sampled from some distribution. And to recover the true support of x bar, ideally we would like to find a small support which covers the true support of x bar. We study sparse linear regression under the RSC assumption for an algorithm, orthogonal matching pursuit. Orthogonal matching pursuit is an incremental and greedy algorithm. It is very popular and easy to implement, and is also widely studied in the literature. The known bounds for sparse regression algorithms had large gap in their upper and lower bounds for the generalization error. The known upper bounds were proportional to square of condition number, whereas the known lower bound held conditionally for polynomial time algorithms and proportional to condition number. In this work, we show that the generalization error bound for OMP is in fact kappa tilde log kappa tilde, and we show an unconditional lower bound for OMP. We also provide results for the support recovery guarantees for OMP, along with providing its lower bound. The known results on support recovery for sparse regression algorithms require a support expansion level proportional to kappa tilde square. In this work, we show that OMP can achieve support recovery in only kappa tilde log kappa tilde times S star iterations. Here we would like to discuss a key idea of the work. We show that if after a reasonable number of iterations, if there is any support unrecovered, then there is a large additive decrease in the function value. And because the function is non-negative, in fact, we can show that the function can be properly lower bounded by a positive quantity. Support recovery will happen very soon. And one can easily show that support recovery with a small support implies small generalization error. Thank you. We hope to meet you at a poster session. Our poster number is 63.
Okay. That's it for the session. That's it for the session.